points, directions, and then we saw planar density, linear density, and at the end we said that okay, I will be discussing related to the defects in solid. So whenever we want to say okay, an idealized solid, it means that this solid has perfect order. So it's having a perfect order. So idealized solid means perfect order which is existing throughout the crystal system. That means real perfect crystal does not exist in this film. There are always some defects or imperfections. So many of the important properties of the materials are due to the presence of this imperfection. So these properties are arise because of this defects and imperfections. So that's the reason we are going to study what are the different types of defects. So defects generally are classified into 4 categories: point defects, linear defects, planar defects, volume defect. So when I say volume, it is an 3D defect. So planar, it's an 2D defect, linear, one dimensional, and it's an zero dimensional defect. So it's a point defect. So whenever we say point defect, that means it's related to one single atom. So atom which is going to be misplaced or missing. So atoms missing or in irregular places in the lattice. That is point defect. Linear means a group of atoms. So group of atoms, say missing or irregular position. Planar, that means the whole plane of atoms, which is going to be the interface between the homogeneous regions. That means it can be related to the surface or due to the grain boundaries, because that is the particular plane of region. And volume defect, 3-dimensional, it is nothing but the extended defect of all these 3, which is like example pores and cracks. I may not go in deep this volume defect, because volume defect is something which is pores and cracks, which is always visible with a macro vision. So this will not discuss much. Other things we will see what are these different defects. So if you see this diagram, there are a lot of defects in this, which is point defect, linear defect, and plane defect also. So here if you see, one atom is missing. So that type of is called as vacancy. So here if you see, this is one extra plane of atom. So this is plane, other plane. So this is an extra plane of atom which is there. So it is a linear defect. So like this, there are different defects. Here if you see, this one is an interstitial defect. So interstitial atom is inside. If you see this one, this is another atom than the normal atom. So it's a substitutional atom which is placed, and this can be a bigger size or of smaller size. So that is also possible. So these are all different defects. So we'll see one by one now. So point defect. So first one is your vacancies. So vacancy means nothing but it is a vacant atomic site in a structure. So if you see this diagram, this atom is not there. So this is a missing atom, and this region is a vacancy defect. So the vacancy is created when the atom is not there. But thing is in atom is not there, it has to go somewhere else. So maybe it is going to some other places and sit in an interstitial position. Then it is an self-interstitial atoms. So this atom is sitting in some other region. So in the background of this, what you see. So this is an extra atom position between the atomic site. So whenever this is going to happen, it is going to lead to distortion of planes because of the hindrance of the other atom in the particular lattice points or the interstitial points. So whenever we say about vacancy, okay, there is a normal vacancy, but if you increase the temperature, the atoms are free to vibrate because they are getting more energy, and since more energy is there, and upon a particular threshold energy, the atoms are going to move out from its lattice points. So the moment it is going to move away from its lattice point, that means more number of vacancies are going to be created with increase in temperature. So if you increase the temperature, the vacancy is also increasing. So this is that. So equilibrium number of vacancy for a given quantity of material depends on and increases with the temperature, and the formula for this is NV equal to N exponential of minus Q V by KT, where this N is the total number of atomic sites. This QV is nothing but the energy which is required to form the vacancy, that is the threshold energy which is required for the movement of the atoms from its lattice point, that is creating the vacancy, and T is the temperature in Kelvin, and K is the Boltzmann constant, where the value is 1.38 into 10 power minus 23 joules per atom per Kelvin. So based on this formula, we will see one problem now. So we need to calculate the equilibrium number of vacancies. Do you want me to solve the problem, or we directly go with theory?
Can we solve one, sir, for practice?
Okay. So calculating the equilibrium number of vacancies per cubic meter for copper at 1000 degrees Celsius. The energy for vacancy formation, it is given as 0.9 electron volt per atom. The atomic weight and density at 1000 degrees also given, that is 63.6 grams per mole and 8.4 grams per cubic centimeter respectively. So if you see what are the things necessary, we have to first find it out. So the problem may be solved by using 4.1, which is already before we know the density equation. However, to determine the N, the number of atomic sites per cubic meter for copper from its atomic weight, its density, and however number has to be calculated. So do you remember this equation? Yes or no? Should I show that equation again?
Yes.
So it is the density equation. Okay. So if you take the density, we get mass by volume, and based on that we can calculate N by Na equal to rho by A Cu. So if you see, rho is equal to N into A divided by Na. So this is the density equation where we calculated theoretically. The same equation we are writing in this form based on the N, which we need to calculate the number of atomic sites per cubic meter. So once we calculate this by substituting the Na density value and the atomic weight value, we get the number of atomic sites. So we find, after substituting the values, 6.022 into 10 power 23, 8.4 and 63.5, we get the number of atomic density values are 8 into 10 power 28 atoms per meter cube. So these are the number of atoms which is available in the per meter cube. Now we need to calculate the number of vacancies at 1000 degree. So then we will use this formula, since we know QV, T and N. So N we already calculated because these are the number of atoms per cubic meter. Q is also known, that is 0.9. K is 8.16 10 minus 5 and T is 1200 Kelvin. So here it was given as degree Celsius. We need to convert to Kelvin. So plus 273, we put 273 Kelvin. So if you try to solve this, you will get NV equal to 2.2 into 10 power 25 vacancies per meter cube. This one you need to remember based on the theoretical density. Sorry. Right. So you need to calculate based on the density. So the next type of point effect is impurities which are going to be in the solid. So if you take same number of atoms So if I divide this, so this is an idealized solid structure where these are the atoms around the on the lattice points. But thing is, it is not so. Always there are some other impurities based on the system. So what are type of the impurities we can have? We can have other atoms which are of the similar size of this atom, and they can take the lattice point, or you can have another solute atom which is going to be smaller in size, much smaller in size, and they may take the interstitial size. So but whatever other solute atom is going to come inside, they are nothing but they are the impurities of the system. So two possible ways are there. There can be larger atoms also and much smaller, which is going to sit in the interstitial. If the atom is going to be much larger, then there is going to be some tension and compression around the lattice points surrounding that particular atoms. So this type of impurities are with respect to an atom is also called as an point defect atom, and they are nothing but the impurities in the solids. If the atom is replacing the lattice point, the original atom, if it is replacing the original atom in the lattice point, then it is called as substitutional solid solution. And if an atom is not going to replace the lattice point, but it is going to sit in the interstitial site, then it is called as an interstitial solid solution. So that is the difference between substitutional and interstitial. So when does this happen? If they are in the similar size and replacing the lattice point. So for example, if you take copper and nickel, if you take nickel are the blue ones and the copper, which is the green, which is the solute atom. So the copper atom, if you see the size of the copper atom, it is much more similar to that of the nickel. So this copper can replace the atom of the nickel. And if you take carbon, carbon is 10 times smaller than that of the iron atom. So the carbon always takes the interstitial sites, and this type of impurity is called as an interstitial solid solutions. So these two example, why specifically taken, not other one is, you will read this also, you will read this also later on. So iron carbon, you will see this one, copper nickel, again phase diagram you will see later on. One more thing is nickel copper, if you take, both are having FCC crystal system. So there are different criteria, other impurities which can sit inside as a solute atom in an original crystal structure. So if the substitutional atom is smaller than the original atom, then the lattice is in tension, and if the substitutional atom is going to be larger than the original atom, then the lattice is in compression. So to understand this very simple diagram, so 1 diagram, 2, 3, 4. So if I make a smaller one here, which is sitting in the lattice points, that means it is going to pull inside the lattice inside. So this is what it is. So if it is smaller, it is going to pull the surrounding lattice points towards it. That is called as a tension. And if the atom is going to be larger, so if this is larger, then it will try to push the lattice point outwards by making it as compression. That is what is compression. Then comes defects, point defects in ionic solids. So when we talk about ionic solids,
Excuse me,
it
sir.
is necessary. Yes, please.
Sir, a bigger size atom can also fit in the interstitial space.
Hey, interstitial space cannot, man. This is, I am taking the lattice point itself. So now if this point you see, 1 minute. So my diagram is very crude, I know. There are same diagram is available later on, we'll show that also. So now if you take, these are the atoms, right? 1 atom, 2 atom here, 3 atom here. So these are all like the atoms, and if it is exact same size, not a big deal, right? But now if this is smaller, say this one is a smaller one and it is taking the lattice point, right? It's not too small, it's smaller than the original atom site of the original element. Thing is, now this space is there, no? So these atoms will be free to go inside. So it is going to pull inside. All these are lattice points. The atoms are sitting in the lattice point. So this is the lattices. So these are going to be pulled inside. So tension is what? It is nothing but pulling of the material. So this is what it is happening. So this surrounding lattice is experiencing an tension. Now,
Yes, sir. Got it, sir.
okay?
Yes, sir.
Okay, it's not easy to understand one time, I know that. So that's the reason I drew it very crude, but still it's fine. So for others, again, now if this atom is going to be big enough than the green, so it has to sit inside. So it is going to push all this atom, it's going to push. That means it's going to press towards the other direction. That is nothing but now it's in the compression state. So that is what this statement means. So the next one is your defects in ionic solids. So in point defects in ionic solids, one thing we should know that in ionic solids, the electron neutrality is always maintained. That means the both positive and negative charge are of equal numbers. So total maintaining as 0. So this has to be always maintained with respect to ionic solid. So point defects in ionic solids, we have Scotty defect and Frenkel defect. So when we say Scotty defect, that means you have an cation vacancy and an ion vacancy. So it's a pair of vacancy. If you see this region here, so one cation is missing and one anion is missing. Considering this is +1, this is -1. This +1 -1 is only for you to understand. If this is +2, then there should be 2 negative ions going out. Then only the electron neutrality will be maintained. Okay. The next one is your Frenkel defect. So you have a cation vacancy and an cation interstitial pair. Nothing but this cation vacancy is there, and this cation is going and sitting in the interstitial site somewhere else. So this is represented here. See, this blue one is sitting in the interstitial site. Then this is an Frenkel defect. So if say this is all minus, 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 and this is all plus, say plus, plus. So maybe this is Na and this is Cl, right? So if I remove this Na and place it with Ca2+, so what will happen? So I'll get one positive more. So that means one more chlorine will be there extra. So one more chlorine will be there extra. Or if I put Ca+2, then one Na is also gone. So 2 Na gone and only one Ca plus there. So then you get a vacancy here also. So this is also an ideal way where you can say that how these atoms play an important role in the defect. Okay, this is expressing the composition of an alloy in terms of the elements which are present in the system. This is only a now 2 element system where we have element 1 with mass m1 and element 2 with mass m2. So if you want to calculate the weight percentage or mass percentage of the total alloying system, so it's nothing but the weight of a particular element relative to the total alloy weight. So if there are a number of boys and girls in the class, so I want to find the percentage of boys. So what is the formula you will use? Hey guys, this slide you don't see, man. My question you understand, man. So in a class there are total number of students are there, boys and girls. If I want to know the percentage of boys, what will be the formula?
So number of boys divided by total students into 100.
That's it. The same thing is written there. The same way you have to find the weight percentage of an system of a particular composition. You can have atom percentage also. It's based on the number of atoms. Only thing is, please remember this formula for you. So to find the number of atoms, it is nothing but mass divided by the atomic weight of the element we should know. Then you can calculate the atom percentage also. So you can convert atom percentage into weight percentage or weight percentage into atom percentage. There are some formulas related to that for conversion. Have a go through it. There is a big derivation in your Calister. If you are interested, open the book and see it. Okay. And next comes your one-dimensional defect, that is the linear defect. So in linear defect, it is nothing but an series of atom which is going to be an extra series. So if you see this particular diagram, this whole plane of atom is an extra plane of atom. So this is an defect. Okay. So this is a one-dimensional defect. So the one-dimensional defect or the linear defect you can quantify. So once you quantify, then it can be quantified in terms of Berger vector. So how does you quantify and defect, one-dimensional defect by Berger vector? So there is a method for that. So you always have to go in all directions like this. So your starting point and ending point should be same. So how many steps you go each? So if you go 1, 2, then down 1, 2, again in this direction 1, 2, and top 1, 2. So if the starting point and the ending point are same, then there is no defect. If there is a difference, then that atomic length is your magnitude of that particular defect. So if I start from here, say around 3 steps in each way. So this is 1, 2, 3. Now I go down 1, 2, 3. Now backwards 1, 2, 3. Now upwards 1, 2, 3. So this was my starting point, this was my ending point, but thing is it has not reached the starting point. So this atomic length is the magnitude of the defect and it is denoted by Berger vector. Okay, I have not yet come to the original edge defect, only to say when you have to say it's a linear defect or not, and this is the magnitude. So you get two types of defect. One is this edge defect, that is the edge dislocation. The other one is an screw dislocation. So when do you say it is an edge dislocation and when do you say it is a screw dislocation? It's based on this Berger vector angle with the dislocation line. Okay. So this dislocation line is nothing but the plane on which these atoms are moving, or now if you see the screen, So considering your vision is a straight line, and that is the plane on which the atoms is above is going to move. So if this is going to be your vision from your eyes to the monitor, that is a straight line, and you see that the Berger vector is in this direction. So if you see the angle between the straight line and the Berger vector, it is 90 degree. That is nothing but it is perpendicular. So if the angle between the Berger vector and the dislocation line is perpendicular, then you call this as an edge dislocation. And the moment the Berger vector is going to be parallel to dislocation line, then it is going to be screw. So please understand, previously I was talking about point defects and everything, but when I came to this linear defect, I was not using most of the term like defect, but rather I was using dislocations. So whenever we talk about linear defects, we use the terminology with respect to dislocation. Why dislocation? Because it is nothing but the plane on which the atoms are going to move. Whole series of atoms are going to move. That's the reason the dislocation terms are more important when you are using with linear defects. So based on this only, if you are able to move the dislocation, that means your material is ductile. If you are not able to move the dislocations, or the dislocations are stuck or pinned, that means your material is becoming brittle. So this is how the ductility and brittlity of brittleness of the material can be set. So coming back to the topic, so when I say edge dislocation, the Berger vector is perpendicular to the dislocation line, and if it is parallel, it is going to be screw dislocation. So now in this diagram, if you trace the atomic plane around the screw, it will make sense, spiral or a helical path like a screw, and hence the name. So if you try to so this black line is nothing but 1, 2, 3. If you count and see, it's the same. Only thing, the starting point and the ending point are not same. So this is your Berger vector in this direction, and this region is your vision, which is nothing but the dislocation line, and this dislocation line is parallel to this Berger vector. So that's why it is called as a screw dislocation. So it is something like you have this cubes, 9 by 9 cubes or 3 by 3 cubes. So if you tilt it and you see it from the side, one set of the cube is little bit tilted, tilted. So in the center, if you keep it and see it from this direction, so this is going to be your line, and this is going to be the defect, how much you have moved around the rubric. So this is a screw. So I said it is perpendicular, parallel. So Berger vector, dislocation line, edge. So dislocation line, screw. But if it is neither perpendicular or neither parallel, then it is called as mixed dislocation. That means both are there in there. So this is what it is. So you have perpendicular in the positive direction and in the negative direction, right hand screw or left hand screw. These are parallel. So this is your screw, and this is your edge, but everywhere around this region it is neither perpendicular nor parallel. So this particular loop is called as dislocation pole, and this region which is neither perpendicular called as mixed dislocation. So representation with an diagram to show that it is neither parallel nor anti-parallel or not positive perpendicular or negative perpendicular. Then it is a mixed dislocation. So compilation of all that one is denoted here. So how does this dislocation or the edge dislocation is going to move? So when we apply a shear stress, so I said this dislocation line is nothing but your slip plane where the atoms on that it is going to move. So this is the shear stress which is going to be applied. So when you apply this, new bonds are formed and old is broken. So stepwise everything happens. So initially A is bonded, afterwards B is bonded, and at last this defect comes to the surface, and based on that we can say it is an unit step of slip or double slip of slip. So this type of motion, if you say it is nothing but a dislocation motion, and it is similar to an caterpillar movement where you get an incremental breaking bond. So you get a new bond formation and old bond breaks. So this breaks, you get a new bond, and then it comes to the surface. Whether it is going to be edge or screw, whether it is going to be edge or screw dislocation, whenever we talk about the macroscopic deformation, which is going to be on the surface of the material at last, always end up in the same way. So this is with respect to edge, and this is with respect to screw dislocation. So if the material or the loop is going to go bond, then you get on the surface, right? So this is what you get it on the surface of the material. And if you try to do screw, so by applying the shear stress, so this will cut and then it will form again. So again you get on the surface. So if you see in both, the macroscopic deformation is same whether it is going to be in edge way or in the screw way. Only thing is you should know that the plane in which the slip is going to occur, that means the atom is going to move. So in which plane the atom is going to move is based on the number of atoms on that particular plane. So if I have, say, in a plane the atoms are arranged like this, and there is one more plane in which the atoms are arranged like this. So whether the slip will move better in this one, first one, or in the second one? Answer?
The first one.
Yeah, it is understood. So with the diagram you are able to say it very clearly. So the only reason is the atomic density, to be very much specific. Okay, the atomic density here it is higher than this region. So that's the reason it is going to move in this particular plane. So there's, for any movement to occur in a plane or in direction, it has to be the highest atomic density, and that only the atoms will move, and that is the region where it is called as a slip plane or slip direction. We already know this is a plane in a unit cell, or it can be a direction which can be there. So if you can recall our crystallographic points and direction. So I'll draw one cube now. X, Y, this is my origin. So this is an FCC atom, okay? FCC I am putting. So I am going to draw one direction. What is this direction? Miller indices 0, 1, 1, right? So if you see this in this particular direction, 1 atom, 2 atom, 3 atom. And if I have this one, so 1 atom, 2 atom. So in this, the slip will occur. That means any stress or any load applied in this point can easily move in this one rather than this one. So this is way how it is going to happen. Similarly for plane also. So in one particular plane there can be different directions. So again we talk about compression and tension. So this is the extra plane of atom. So since it is extra, this surrounding is in compression. Since there is more space, this is in tension because it is pulled towards this direction, inwards. So this is in tension and this is in compression. Previously we saw with respect to one atom, now we are seeing with respect to extra plane of atoms. So the next terminology is your slip system. So what exactly is slip system we will see now. So dislocations do not move with the same degree of ease on all crystallographic planes of atoms or in crystallographic directions. Okay, so they do not move with the same ease or same degree in all planes and in all directions. So they have a preferred plane and a preferred direction in which the dislocation will occur. So the preferred plane, it is called as slip plane, and in that slip plane the preferred direction is called as an slip direction. Okay, so this combination of slip plane and slip direction both together is called as an slip system. Okay, and now if you take the family of 111 plane, so we take the family of 111 plane. So when we talk 111 plane, this is nothing but the triangle, so diagonal line and then tilted towards the z axis or any other corner, or it can be in this direction also. This is also 111, and if you take this one, this is also 111, and this is also 111. It's too crude, so we'll take only one particular 111 plane. So you have 4 111 planes in an unit cell. Okay, so in this 111 plane, if you see, that is the A, C, F, E, D, B. This particular plane, if you see, this is in the atomic structure in the 2D form, it is drawn here. Atoms are closely packed, so in this particular plane the dislocation will move. So if you apply any load here, stress here, so then the atoms can move in this direction or in this direction in this particular plane. It cannot go in other plane. Why? Because this is the one which is going to have higher atomic density. So then it can go in A, B, D way, or it can go in A, C, F way. So two possible ways. So once it has selected A, C, F, then it can go from F, E, D, or else it can take A, B, D and then D, E, F. So possible is one plane, it has one direction, two direction or three directions possible. So totally there are 4 111 planes in the family of this one, and in each 111 there are 3 directions possible. So since 3 direction each, that means there are possibility 12 slip systems available for 111 family of direction. So this is what it is mentioned here. For FCC cubic unit cell, there are 12 slip systems, 4 unique 1-1 plane, and within each plane 3 independent directions. Understood this one?
Yes, sir.
Yeah. So because this you should know why it is going to take only 1-1-1 and not other thing with respect to plane, not direction. So if you think why not possible means you should check now with some other plane and see what is the problem with that. So if you want, we can take one more plane and I can see. So if I take this particular plane, so what is this plane Miller indices? Anyone? Or maybe, wait, it's not so clear. So I'll take the top one, right? Now tell me what is this plane? Zero, 1, right?
0,
0, 0, 1 without intersecting in Z direction, right? So now if you draw the structure for this in this way diagram, 1, 2 atoms here, 3 atoms here. So there is space in between. So if you apply any load here, it cannot go very easily here. So maybe this atom is moving up to this only, and it's not going to this particular point. So this is not an high atomic density plane or direction. So that's the reason it is not going to occur in this one. If it has to occur in this one, then the load is much more higher than the original load. But thing is, before whatever you are going to apply load, if this plane is there, no, so this will be there. So the moment you apply that load, it will try to go through this particular 1-1 plane only first, and then it will move. The stress or the atoms will move, or we can say the dislocation will move. Moment the dislocation is moving, your material is ductile. Moment the dislocation is not able to move, or it is going to hinder the movement of dislocation, then the material becomes strengthened and it's going to go to the brittle state. So I will stop with this. I think I am going deep inside the topic. Okay, with this I stop the class. It's already 50.